Is everyone ready? Let's get ready for chemistry! If we were to put some zinc metal in a solution containing silver ions, the net reaction would be that the zinc would turn into ions and the silver would plate out. Now the silver would start coating the piece of zinc more than likely. Why? If you take your two reduction potential reactions and you rearrange them like this, when I flip the zinc reaction, I change the sign of the cell potential. Then if I add these together, I get 1.56 volts. Now that's great. What's more important though is that this is positive. A positive cell potential means that the reaction is spontaneous, or if you're taking the AP chemistry test, thermodynamically favorable. If the cell potential is positive, the process will be spontaneous, and that's thermodynamically favorable. Great, but you won't be able to get any useful work out of this. The way we've got this set up, there will be a transfer of energy, but you won't be able to get it to do any work. It would be like turning 100 sugared up toddlers loose in the yard. Sure, they've got a lot of energy, but you're not getting any work out of that. If you were to hitch all of those toddlers up to a sled, let them pull a sled, you would get work out of that energy. So what we can do is we can decouple these two reactions. So we'll get two beakers, and in one beaker, we'll put zinc, and then another beaker, we'll put silver. If we connect them with a wire, when they transfer electrons, we can make those electrons do work for us when they pass through something. So if we decouple the two reactions, when the reactions happen, they'll do work. Now we've got our half reactions. We should write underneath the beakers that they belong to. This one will be Zn goes to Zn plus 2 electrons. And then this one will be Ag plus electron goes to Ag. Now why will it go this way? Because when I add them together this way, I get a positive cell potential. So this is going to want to be a spontaneous process. This is going to want to be thermodynamically favorable. So the reaction that will happen will be the one that has the positive E naught, the most positive cell potential. So it'll work like this. I can use these pieces of metal as my own electrodes. If the half reaction involves a metal, that's not, like an alkali metal that's just going to explode when you put it in water, then I can use that piece of metal as an electrode. If I can't use that piece of metal as an electrode, if it's not metal, I could use a graphite electrode instead, a piece of pencil lead or something like that. What this is going to do is this is going to produce electrons. And what this is going to do is this is going to require electrons. So the electrons are going to travel from where they're being produced to where they're being used. If I did this, nothing would happen. The reason nothing would happen is that's not all that's in here. There's also some spectator ions present in solution, both to make the solution conduct electricity and to balance the charges of the cations. At this electrode, we see that this beaker is going to become more positive as time passes. As this beaker becomes more positive, we will need more anions to go with those cations that are being produced. If we can't produce more anions to go with those cations, it simply won't do anything. Here, we're losing cations. As we lose cations, we're going to have an excess of anions, of spectator anions. As those spectator anions build up in this beaker, the reaction will stop. So what we need to do is we need to be able to transfer those anions from where they're no longer needed to where they are now needed. What we need is a salt bridge. A salt bridge has some sort of a semi-permeable membrane in it, a cotton ball, or maybe it's filled with agar, like you use to make Petri dish plates, right? Some kind of semi-permeable membrane that will allow the ions we want to pass through, but not the metal ions. We don't want them to pass through as much. So it's usually filled up with some sort of spectator ion type solution, something that's not going to want to be oxidized or be reduced. If the electrons are moving this way, if the electrons are moving to the right, then the nitrate molecules are going to want to move to the left. So the anion, the spectator anion, will move in the opposite direction that the electrons are flowing. Now, if the nitrate is moving to the left, then the potassiums are not needed there anymore, and they'll flow to the right. This is the oxidation half reaction, because oxidation has electrons in the product side. This is the reduction half reaction, because it has electrons on the reactant side. Now, a lot of textbooks say oil rig. That never made any sense to me. My preferred method of remembering which one is which is OIP rear. Reduction is reactants. Those two start with R's, so it makes it easy for me to remember. Where the reduction reaction is happening, that's the cathode. Where the oxidation reaction is happening, that's the anode. And since these things both start with vowels, it's easy to remember anode and oxidation. And since these things both start with consonants, it's easy to remember reduction and cathode. Or you could do an, ox, and a red car. That's another way that you could remember them. Anode is oxidation, reduction happens at the cathode. This thing is a galvanic cell. It's a galvanic cell because it's spontaneous. So an electrochemical cell that's spontaneous is a galvanic cell. Adding these two half reactions together right now would give us a positive cell potential. But we can't add these two half reactions together right now, because they're both reduction reactions. Now get used to this one. Most reactions, most electrochemical half reactions that are tabulated as reduction potentials. So one of these guys needs to flip. And the one that flips for a galvanic cell is the one that's going to produce a positive cell potential by the time it's done. So what we need to do is we need to flip this one. To make these half reactions add together, I need to multiply the top half reaction by 5. When I multiply the top half reaction by 5, that does not change the cell potential, and I'll talk about why in a different video. So the cell potential stays 0.77 even though I multiplied it by 5. But flipping it around switches the sign. So the cell potentials add up to 0.43 volts. So this thing will produce a voltage of 0.43 volts. Let's draw a galvanic cell for this. So let's get 2 beakers. If I used an iron electrode, it might interfere with the half reactions. So since there's no metal involved in this, let's just make both of these electrodes out of graphite. Graphite electrodes are nice because they conduct electricity, but they're pretty non-reactive. In one beaker, I'll have iron ions, and in the other beaker, I'll have iodate, and that will be becoming iodine. We'll write the half reactions underneath the beaker they go to. And they're big and fat half reactions, so it's a problem. As a galvanic cell, we'll get some electromotive force out of this. We could measure the force that we're getting using a voltmeter, and it should tell us that it's 0.43 volts. Now, as this reaction runs, we'll run out of reactants. As we lose reactants, we'll lose electromotive force, because the G of the reaction is dependent on the concentration of the reactants. So as we lose reactants and gain products, the reaction will lose its ability to do work. Okay, electrons are produced here. So the electrons are going from this electrode to this electrode, where they're being consumed. For this to operate, it would also need a salt bridge. To allow the ions to flow from one beaker to the other. If the electrons are flowing to the right, then the spectator anions would need to flow to the left. If the spectator anions are flowing to the left, then the spectator cations would need to flow to the right. So that's the function of my salt bridge. It prevents the buildup of charge in a beaker. Then we would want to label the anode and the cathode. The electron is on the right side, that's the oxidation reaction, so this would be the anode. If the electron is on the left, that's the reduction reaction, so this would be the cathode. You'll notice that this is acidic. So at the cathode, the solution, its pH is going up. As the acid is consumed, its pH is increasing. So that's a galvanic cell involving these two half reactions. Let's take these two half reactions and let's draw a galvanic cell. Now they're both reduction potentials, so one of them needs to be flipped. The one we flip is the one that, when the two equations are added together, will give us the most positive result. So I want to flip this one. When I add these together, I get a positive 1.10 volts. So how much potential does this cell have? 1.10 volts. If I want to draw this as a galvanic cell, I'm going to start with two containers. I can use the metal as its own electrode for this. It'll need a wire connecting the two. And this thing can power some sort of, I don't know, maybe a light bulb. That's what a light bulb looks like. Get over it. And then they'll need a salt bridge connecting them as well. And then this thing would also have some copper ions in it as reactants. And then this thing would also be producing some zinc ions. So we'll write the half reaction underneath this. Zinc goes to zinc plus 2 electrons. And then the half reaction for this one, copper plus 2 electrons, goes to copper. The electrons are being consumed on the right side. So this side will be the side that needs the electrons. And this side is the side that's producing them. So the electrons are going to travel to the right. And if the electrons travel to the right, then the right side is becoming more negative. So the negatives need to go somewhere to maintain charge neutrality. So the anions will be traveling to the left. And if the spectator anions travel to the left, then the spectator cations will travel to the right. Label the anode and the cathode. If this thing has electrons on the reactant side, then it's the production reaction. That would make this the cathode. If this thing has electrodes on the product side, then that would make this the oxidation, and this thing would be the anode. And if you were to measure the electrical potential of that wire, it should come out to be 1.10 volts. The other thing they could ask you is, how is the mass of the electrode changing? Since this one is solid zinc becoming zinc ions, the mass of the solid zinc is decreasing. So the solid metal zinc electrode is becoming zinc ions. This one, the copper ions are becoming solid copper. Those copper ions will become solid copper on the electrode. They'll plate onto the electrode, they'll increase the mass of the electrode. So that's a galvanic cell involving zinc and cupric. That's what it would look like. You would need to identify the anode, the cathode, the salt bridge. You would need to have a couple of electrodes. You would need to have a wire connecting the two. You would need to show the movement of electrons. You would need to show the movement of ions in the salt bridge. A galvanic cell is spontaneous. So the two reactions, when added together, should give us a positive cell potential, a negative Gibbs free energy.